Section: Introduction. In this section, we discuss the challenge of catastrophic forgetting that arises when we fine-tune deep learning models on new tasks. This issue is particularly significant in continual learning scenarios, where we receive a stream of tasks that may not repeat. We need fine-tuning methods that enable our models to adapt to new information without losing previously acquired skills. Research has shown that large language models, LLMs, can perform worse on earlier tasks as they learn new ones. Additionally, these models can forget general knowledge, not just information tied to specific tasks, and the severity of forgetting tends to increase with model size. Current leading strategies to reduce forgetting mainly focus on adjusting the training data during fine-tuning. These strategies either keep a buffer of past task data or create approximations of that data for training alongside current tasks. However, both approaches come with drawbacks. Data buffers require significant memory and management, while generating data approximations demands extra training and computational resources. Traditional continual learning methods often involve adding penalties to the training process to limit weight changes, but these can also be memory-intensive since they need to store multiple copies of model parameters. Recently, new techniques have emerged that aim to address forgetting without using buffers or excessive computation. Yet, in situations with many tasks or significant variations, these methods often struggle to effectively balance retaining knowledge from previous tasks while learning new ones. Building on the efficiency of these approaches, we propose that model averaging should not be limited to just the end of training. Instead, we explore whether averaging partially trained models can help reduce forgetting and enhance performance on new tasks. Inspired by L2 regression, we introduce sequential fine-tuning averaging, SFA, a method that merges the model currently training on a new task with a checkpoint from a previous task during the training process, rather than only at the end. We also define a concept called averaging frequency, which allows us to control how often we merge during training to balance performance on past and new tasks. Our approach has the advantage of not needing to store past data, as it uses previous model checkpoints as substitutes for that data. Our experiments show that by incorporating averaging during training, our method consistently outperforms other merging techniques that only merge at the end, achieving better results across all tasks. We systematically investigate forgetting in two main scenarios. 1. A traditional continual learning setting with a long sequence of image classification tasks, and 2. Fine-tuning pre-trained LLMs on very different domains like law, math, and code. These scenarios help us evaluate SFA under both standard continual learning conditions and in situations with significant task differences, testing its robustness to domain shifts. Our contributions can be summarized as follows. We introduce sequential fine-tuning averaging, SFA, a method that enhances model merging techniques. Section Summary. In this section, we discuss the challenge of catastrophic forgetting in continual learning, where deep learning models struggle to retain knowledge from previous tasks while adapting to new ones. We introduce sequential fine-tuning averaging, SFA, a method that merges models during training rather than at the end, allowing for better retention of past knowledge without the need for data buffers or additional training resources, and demonstrate its effectiveness across various tasks and domains. Section: Methodology. Sequential fine-tuning averaging, SFA. In this section, we introduce our method called sequential fine-tuning averaging, SFA, which builds on existing model merging techniques to reduce forgetting in continual learning. Our approach involves taking a pre-trained model and fine-tuning it on a series of tasks. While fine-tuning on the current task, we periodically average the model's parameters with those from a previous checkpoint that was fine-tuned on earlier tasks. Specifically, we denote the parameters from previous tasks as theta_O, and the parameters after a gradient step on a new task as theta_t+1. Every certain number of iterations, as well as at the end of fine-tuning, we reset the parameters to a weighted combination of theta_O and theta_t+1, where the weight is controlled by a hyperparameter between 0 and 1, typically set to 0.5. We demonstrate that our method approximates L2 regression, helping to maintain the model's performance on past tasks by preventing significant shifts in parameters. Our technique integrates ideas from continual learning, rehearsal, task arithmetic, and WISE FT, but differs by using a model fine-tuned on past tasks instead of storing data in a buffer. Additionally, we merge a past checkpoint with the current model rather than combining task vectors from different models. Our method focuses on merging during fine-tuning across tasks, while WISE FT merges a pre-trained model with a fine-tuned one. As we encounter more tasks, we continue to average the most recent high-performing model with the current parameters, updating the past model to reflect the merged results after each new task. To evaluate our method, we fine-tune models on a series of image classification tasks and 3 distinct language domains: law, math, and code. We create a stream of 20 tasks from Food 101 and CIFAR 100, grouping labels accordingly. For the language domains, we use specific datasets that contain domain knowledge and unique tasks. We aim to test our model's ability to generalize across these diverse domains to assess the effectiveness of our method under significant shifts in knowledge. We define forgetting as a drop in performance on a task after fine-tuning on a new one. To measure this, we use specific metrics and holdout sets. In our experiments, we first fine-tune models on image tasks while applying various strategies to mitigate forgetting. We establish a baseline by fine-tuning the initial model on all tasks simultaneously, which is not feasible in a continual learning context. Sequential fine-tuning without intervention leads to low accuracy due to forgetting. To address this, we implement 2 variations of rehearsal with data buffers of different sizes. However, data buffers have drawbacks, such as increased storage costs and potential privacy issues. Therefore, we explore model-based methods like task arithmetic and WISE featuring. We find that SFA, which merges a partially trained model with the initial one, generally outperforms these methods. Our results show that SFA, especially when averaging occurs near the end of training, achieves better performance than methods that average only at the end. This indicates that averaging during training is more effective, as it allows the model to continue learning after the averaging process. Finally, we analyze how averaging affects performance during training by tracking accuracy across tasks. We compare models fine-tuning without intervention to those using SFA. Our findings reveal that SFA helps maintain past task performance while introducing new tasks, highlighting the benefits of our approach in continual learning settings. Section Summary. In this section, we introduce sequential fine-tuning averaging, SFA, a method that combines a pre-trained model with averaged parameters from previous tasks to reduce forgetting during continual learning. We demonstrate that SFA effectively preserves performance across tasks by periodically merging model parameters, outperforming traditional methods like rehearsal and task arithmetic in various image and language classification tasks. Section: Testing Method Robustness, Mitigating Forgetting from Cross-Language Domains. In this section, we examine the robustness of our sequential fine-tuning approach, SFA, by addressing the issue of forgetting when transitioning between different instruction tasks, like moving from math to code or math to law. We focus on pairs of tasks that are quite different, which allows us to measure the balance between learning a new task and forgetting the previous one. We visualize this relationship on a graph where the y-axis shows the accuracy of the first task and the x-axis shows the accuracy of the second task. First, we confirm that forgetting happens when we fine-tune on successive language tasks. We present our findings for learning math and law using different models, including Llama 2, Qwen 2.5, and Pythia. Initially, we fine-tune our models on a math dataset to establish a baseline performance. This initial model shows improved performance on math but does not significantly change for the second task, which it hasn't been trained on yet. Next, we fine-tune the initial model on the second task, which is law for Llama 2 and Qwen 2.5, and either law or code for Pythia. The results show that while the model performs well on the second task, it forgets much of what it learned about the first task. This shift in performance on our graph indicates significant forgetting as the model learns the new task. For comparison, we also look at the performance of just fine-tuning the base model on the second task. We establish an upper baseline by simultaneously fine-tuning the base model on both tasks, which prevents forgetting and allows good performance on both. To address forgetting in our continual learning scenario, we further train our initial model on a mix of mostly second task data and a small portion of math data. This approach improves performance on the second task while helping to retain knowledge of the first task. We find that increasing the amount of math data leads to better performance on math, but it also requires more storage for the data buffer. However, this method is less effective for Pythia when transitioning from math to code, which we believe is due to suboptimal hyperparameters. Section Summary. In this section, we test the robustness of our sequential fine-tuning approach, SFA, by examining how well it mitigates forgetting when transitioning between dissimilar tasks, such as math to law or math to code. Our findings reveal that while sequential fine-tuning improves performance on the second task, it often leads to significant forgetting of the first task. However, employing a rehearsal strategy with a data buffer allows us to enhance performance on the new task while preserving knowledge from the previous one. Section: SFA on cross-domain data. In this section, we discuss SFA, which stands for Sequential Fine-tuning Averaging, applied to cross-domain data. We start with a model that has been fine-tuned on task A and, while fine-tuning on task B, we average the model weights every certain number of steps, denoted as PT. With the final model from task A, our evaluation shows that as we decrease P, meaning we average more frequently with the initial model, we retain more knowledge from the previous domain. This is illustrated by the orange curve in our figures, where a lower P leads to better performance on math, indicating stronger retention of knowledge from task A, while still allowing for learning in task B, such as law or code. Notably, when we fine-tune on math and then on law, using a P of 0.25 gives us results similar to rehearsal, showing that SFA effectively reduces forgetting without needing data buffers. We achieve this with just two model checkpoints, the initial model and the current one during fine-tuning. Our method also outperforms other model merging techniques like task arithmetic, ties, and wise featuring. In our experiments, we find that task arithmetic and ties struggle to maintain math performance, while SFA with a low enough P retains it effectively. We also explore how SFA scales with more domains. By continuing to fine-tune our model on 3 domains, we find that adjusting P allows us to maintain high performance on the previous 2 domains while learning a new one. In both scenarios, whether transitioning from math code to law or math law to code, SFA consistently outperforms the other methods. To further understand SFA's advantages, we investigate different strategies for adjusting model weights. Unlike SFA's continuous averaging, we look at modifying weights only at the end of fine-tuning. Our findings highlight the effectiveness of SFA's ongoing averaging approach for optimal performance across multiple domains. We find that our default parameter weighting balances past and new knowledge well. We also test if we can achieve similar flexibility by first fine-tuning on a new task and then averaging the final model with the previous one using different weights. Our results show that SFA with AP less than 1 performs as well as or better than the alternative methods. Additionally, we observe that for certain weight settings, other methods fail to retain knowledge from previous tasks, while SFA maintains superior performance. Overall, our analysis confirms that SFA's continual averaging during fine-tuning is crucial for preserving competence across different tasks and domains. Section Summary. In this section, we demonstrate that our sequential fine-tuning averaging, SFA, method effectively retains knowledge from previous tasks while learning new ones by adjusting the averaging frequency, P, with lower values leading to better performance on earlier tasks without requiring data buffers. Our results show that SFA outperforms other model merging techniques and highlights the importance of continual averaging during fine-tuning for optimal cross-domain performance. Section: SFA and L2 regression, intuition for model merging. In this section, we explore various continual learning methods designed to reduce the forgetting of previous tasks by applying a penalty to the training weights. This penalty helps keep the weights close to those that performed well on earlier tasks. Common penalties include L1, L2, and EWC. Typically, these penalties are added to the loss function at each gradient step, which can become computationally intensive as models grow, since we need to load multiple versions of the model weights into memory for each step. We propose a simpler approach by approximating existing continual learning methods through model merging. Specifically, we demonstrate that SFA is similar to L2 regression. We start with the model from the previous task and the model currently being trained. The loss with an L2 penalty can be expressed in a certain way, and updating the model using the gradient of this loss leads to another expression. We can compare this to a scenario in SFA where we average the model parameters after each gradient step. By combining these steps, we arrive at a new form that shows a relationship between our method and L2 regression. Although SFA typically averages less frequently for efficiency, the similarity between our expressions suggests that SFA can be viewed as an approximation of L2 regression. We also provide empirical evidence showing the connection between the L2 distance of the initial and training models in our experiments, and we suggest that SFA may have a Bayesian interpretation due to its resemblance to L2 regression. Additionally, we note that the EWC penalty can also be viewed as a model merging technique. To compare our method, SFA, with existing continual learning approaches like L2 regression and EWC, we conduct an empirical analysis. We train a small neural network on two sequential MNIST tasks, where task A involves labeling even numbers and task B involves labeling odd numbers. We observe that the model's performance on task A declines when it is trained on task B without intervention. In our results, we vary the averaging weight and the frequency of averaging in SFA, finding that higher weights or fewer batches before averaging improve performance on task A. We also analyze L2 regression and EWC under different penalty weights, noting that L2 regression generally performs better than EWC. Interestingly, SFA outperforms both L2 regression and EWC when we optimize the hyperparameters. Thus, SFA not only proves to be computationally more efficient due to less frequent averaging but also achieves better performance without applying a penalty at every step.